Hello, thanks for joining us today for our deep dive webinar series. Today we're going to be talking about line start induction machines and the power quality problems that can be associated with those. My name is Dave Odeman. I'm the product line manager for American Superconductor's DVAR VVO distribution class StatCom. Again, thanks for joining us today. So this is a webinar format. We really want our listeners to take away some key learnings so that this webinar helps in your day-to-day job and as you go about potentially solving these types of problems. So first of all, we're going to visit what is the motor starting power quality problem. We're going to discuss limitations of traditional equipment, automation equipment that has limited effectiveness for solving this problem. We're going to understand the costs associated with power quality related issues, which can be very, very expensive and very surprising. Then we're going to go into the StatCom principle of operation to specifically solving this problem. And then we'll go through some sizing guidelines and other application tips to give you some tools to be efficient in solving these problems. So line start induction machines are the workhorse of our modern industry. So basically, almost any industrial process or industrial application incorporates this technology in some form. Here's a summary view of some of the industries that you might be involved in and some of the applications where these machines will be applied. Quarries typically are using conveyors, large conveyors, as well as crushing operations. Those are all driven by induction machines. Irrigation and water treatment, desalination. There can be dozens or even hundreds of pumps in those facilities, all driven by induction machines. Sawmills and wood chippers are all driven by induction machines. Chemical processing, very commonly pumping processes and compressor processes when it comes to that application. Metal processing, so associated with shredders and cutting, grinding, all driven by induction machines. Landfills and biogas can use very large compressors and multiple stages of compressors at those facilities. And then finally, oil and gas fields, which can be very spread out geographically, having dozens of pumps and wells driven by induction machines. What is the problem and why is it caused by an induction machine? So the problem comes about specifically with respect to line start induction machines, which may or may not have a soft starter, and specifically at what we call the locked rotor characteristic. So the locked rotor characteristic is important because that's the instant when a motor is just started before that rotor is accelerated. This table is actually showing those characteristics specifically. So don't confuse this table with run characteristics. This is showing very specifically the characteristic of a typical induction machine right when that voltage is applied to start it. So we see here this first column that this is the locked rotor voltage and the locked rotor torque associated. You'll note that locked rotor torque is often rated greater than the nominal running torque, typically between 1 per unit and 1.5 per unit, depending on the machine style. And then the last column is the locked rotor current or inrush current. And this is really where the problems start here. And so we've highlighted this column. And the thing to note here is the per unit currents that are associated with this problem. So this literally means that 650% of the rated motor current during run, so 650% of that run current is present during the initial motor starting time. So this is where the problem occurs. Practically speaking, if we think of, for example, a 500 horsepower motor, that would then mean that somewhere around 3 megavars of reactive current is suddenly being drawn from the utilities grid. 1,000 horsepower motor, you're talking over 5 MVAR of sudden inrush current being drawn from that utility grid. And basically, it's a step function suddenly hitting that utility grid. That utility grid has some impedance, and that's why we have this problem. So there really aren't practical utility feeders that that can tolerate this without a significant voltage dip. So it's this locked rotor characteristic that we're stuck with. Induction machines are great, cost-effective machines, very efficient, very reliable, but they do have this sort of Achilles heel associated with them here, and that specifically being the amount of current that they require when they're first started. You'll note that I've also highlighted a row in this table of starting characteristic, and that row shows where typical practice for industry is with motor starters, so reduced voltage motor starters. And a key point here is reduced voltage motor starters are an important technology in the industry, and they're important for managing mechanical stresses on the mechanical equipment. So for example, a gearbox or a coupling, you don't want to damage that or stress it over time, and a reduced voltage soft starter will nicely reduce the torque transient and torque stress that can cause that damage. So we like soft starters for that reason. However, note by this table, it should be very clear that a soft starter typical setting range is not going to address this significant inrush problem that we have. So we just took a 650% problem and brought it down in the 500% range. So that is typically going to be ineffective to solve the problem. So just to recap, we've got a reactive power problem on our hands. It is a fundamental characteristic of the machine. We can't get around it. Reduced voltage soft starting, not going to get us there. So that's why this problem remains challenging to solve. We show an actual event recorded on an actual utility feeder, and this really shows that step function problem that I was explaining. So on the left here, this is actually a voltage recording, medium voltage side of the feeder, when a line start induction machine was started, and you can see about a 12% dip for just a few seconds associated with that machine. And this machine is accelerating pretty quickly, so that dip is shorter in duration. But many of these machines can be starting for 10 seconds, maybe up to 20 seconds. Very clearly a power quality violation, not just that facility experiencing low voltage, but dozens of customers on that same utility circuit experiencing that same disruptive voltage dip. So this really is the type of problem that occurs and why it's so disruptive. On the right now, we're showing, emphasizing this concept of being a reactive current problem. So on the right is the application of a D-VAR VVO StatCom to this particular motor. And the solid blue line now shows the response, the voltage response on that same utility feeder with the StatCom active and compensating that same event. So different day, same event. And we can see that that power quality problem is just totally addressed. And this is now just by canceling that reactive power near the motor. So really emphasizing that, yes, this is a reactive current problem, not a real power problem. If we address that reactive current, then we can nicely expect to solve that problem. So I mentioned the cost in the introduction. So in this slide, we're going to review some applications and what drove the initial expenses due to these problems. So the first application is a brine well pumping operation, and this is an underground aquifer where a naturally occurring salt brine was being pumped for chemical processing. So there were about a dozen motors located across a utility feeder, and these are larger motors in the 1,000 horsepower range. And what was happening is every time this industrial customer would try to start one motor, especially a downline motor, a significant voltage dip would occur, and then that would in turn trip off other either other motors or other equipment associated with their operation. Every time this trip happened, sometimes it would be a short shutdown, but in the worst case, it could actually require a reset of that entire process and have to restart and go through the startup sequence to get back up and running again. Very expensive, typical $50,000 loss per event. And over the course of the year, easily adding up to over $1.5 million of lost revenue in this case. So the real value here was losing productivity, losing that revenue stream every single time this happened. Another example, a landfill gas processing plant. So this is a landfill converted to supply natural gas now in the wholesale market, which is happening more and more with landfill methane. So basically, this is also a case where you just want to keep pumping natural gas into that pipeline and have that revenue stream there. So in this example, the startup of the large compressors in that plant would cause disruptive power quality issues both in the plant and on the utility feeder. And this plant was then required to curtail their startup sequence over a course of about 6 hours to prevent these problems from happening. Well, that's 6 hours of a lot of lost productivity. So every time the plant was either brought down for some service or brought down due to a potential outage, unexpected outage, the startup sequence was much too long. And that resulted in over $1 million in annual lost revenue productivity as well. Last example, a quarry having conveyor loads that are starting. So in this case, it was located on a relatively long feeder, which is not uncommon for a quarry or a mine, which are typically remote, to be fed by a relatively weak grid system. So that problem caught up with this particular customer to the point where they actually had to go off the grid and use a diesel genset and pay the associated costs of that diesel genset providing electricity to the quarry. And about $500,000 of annual expenses to run that genset and then be able to run that motor without causing those disruptions. So very expensive. This can be a very expensive problem, both causing lost revenue as well as increased operating expenses. And then another key point here is it's not just the industrial customer in a lot of these cases. And in all of these cases, and very common, the utility is losing energy served. Anytime these trips happen, anytime there's a curtailment, you can bet as the utility that you could be providing more electricity if these problems were not occurring. So traditional technology. There are a number of traditional automation technologies that have been used in the past, and really none of them are very effective. And the underlying reason why they're not effective is that none of these were designed or created with power quality in mind. They were all created with really automation in mind or motion control in mind. And it's been kind of a secondary byproduct that, okay, maybe they can help a little bit with power quality. So first of all, mechanically switched caps are just simply not fast enough for this problem. They are adequate for motor run compensation if you want some steady state power factor correction. But as we saw, those very dynamic waveforms, just not fast enough to keep up. Another key point where we see people get into trouble, a capacitor near a soft started motor is very likely to encounter problems related to the harmonics that soft starters create. So a soft starter can create around 40% THD in the current. And if you've got a cap nearby, you're probably going to see some spurious fuses getting blown. You're probably going to see some damage to those cap banks over time. So another reason why caps really aren't compatible with soft starters, a key issue to be aware of. Then we have soft starters. We established in that characteristic slide that really it's marginal performance. Really, you can't rely on them. The other problem I just mentioned is they do generate very high harmonics. So while that only happens during the startup, that the level of 40% is enough of a problem that even though it only might happen for 10 seconds at a time, definitely that can disrupt processes. We've seen that happen and that's something to look out for. The last automation equipment that we see being applied traditionally is variable frequency drives. So a VFD does have more effectiveness than a soft starter in this problem. However, it's a relatively complex solution for PQ purposes. And again, it is not designed for solving PQ problems. So again, you're relying on an attribute as kind of like a side effect to help this problem rather than having a piece of equipment that is ensuring and is there to solve the problem. Furthermore, variable frequency drives, if you've got 20, 30 motors at a site, you're going to need 20 to 30 VFDs to solve the PQ problem, and that gets very expensive very quickly. Lastly, people forget this. Larger VFDs in particular do not meet IEEE 519 inherently, and they leave it up to the customer to solve that problem, which can get very expensive, both to study that problem and to then address the problem with the appropriate filtering technique. So just to recap here, none of these traditional equipments were designed or intended to solve the power quality problem. It's all a side effect, and that's really the underlying reason why we still have these problems so common. So now I'm going to go through and introduce a StatCom technology and why it's a nice fit to solve this motor starting reactive VAR problem. So a StatCom, very simply, is an inverter, a power electronics inverter, that is optimized to just process reactive power. So by being optimized to just process reactive power, there are some optimization tricks that can be played that you can't get out of traditional inverter technology. StatComs are capable of controlling voltage, VARs, or power factor, depending on the application. StatComs have been used very successfully and extensively in transmission systems, and their use is growing now in distribution systems as product offerings have now become available for distribution applications. VVO is what American Superconductor calls our distribution class StatCom. So distribution class StatCom is truly distribution class equipment. That's the first key thing to understand. This is not some transmission level product that's kind of tried to quickly apply it to a distribution system. It is literally engineered from the ground up just to operate optimally in distribution networks. So outdoor installation, our VVO StatCom has a nominal nameplate rating of 1 mVAR continuous. That's at 1247. And then it has, importantly, an overload characteristic. And that overload pertains to a 1-minute rating that can happen up to 5 times an hour. We have standard configurations that scale from that 1 mVAR continuous and all the way up to 4 mVAR with the overload characteristic. And then we also offer a metal enclosed inversion when it's prudent to have behind the fence or facility type solution. Lastly, one of the unique characteristics of the VVO is that it's designed with no routine maintenance. So the power electronics have no moving parts at all, 100% solid state design, which allows us to really strip out any of the routine maintenance requirements. What we show here is a StatCom installed in a 15 kV overhead feeder. That StatCom is installed in the existing utility right-of-way. So no land procurement, which is a key advantage in a lot of our projects. On the right, we're showing an installation in a 25 kV feeder, and that does require a step-up transformer to go along with that same H-pull structure that we use. And in either case, we're still staying within that existing utility right-of-way. So a very big advantage in a lot of these projects is to be able to install that equipment in that existing right-of-way, avoid having those expensive potential land procurement requirements or requiring a new easement. This shows some single lines to clarify that we can either connect directly at 15 kV or up to 35 kV when we do have that external step-up transformer. So the key concept to understand with STATCOM inverter technology is that it really does act as a reactive current source to the grid. And so this is where all the benefits really stem from. So it's naturally insensitive to line voltage. So as that line voltage dips, our controller is automatically able to compensate and inject the right amount of current to put it right back up. There are no resonance issues that we get with the passive capacitors. So it's a high impedance device that will not pull in harmonics. And so if you've got a soft starter, or if you have other drives or harmonic creating sources, which are very common at these industrial sites, the STATCOM is going to reject those harmonics and not be sensitive to them. And then the current waveforms that are created by the STATCOM are pure sine wave current waveforms. So well within the IEEE 519 standard for harmonics. You're not going to have to come back and add a harmonic filter. So that gives you a lot of certainty in these projects. You get pure sine wave performance, and that is very important at addressing this problem robustly. Then we have a shunt connection, which makes it very easy to protect. Typically, no outages are taken when the equipment is installed. So much like a shunt cap bank doesn't require an outage, same concept here. And then I mentioned the overload in the previous slide. So that's important for this motor starting application because the overload rating is for 1 minute for the VVO, and most motor starting events are 20 seconds or less. So you can fully specify overload ratings in this application, which really helps to keep the size of the power electronics minimized and further improve the cost effectiveness of the technology. Here's the basic principle of operation applied now. So on the left here, what we're showing is that inductive inrush of current. So we think about this axis here as the reactive power axis, and horizontal axis as the real power axis. So that motor and current is primarily reactive on startup. What the VVO is going to do is automatically inject the offsetting amount of current. And again, it's fully automatic and fully precise. So if you have a 300 horse motor or a 500 horse motor at a site, that VVO is going to automatically determine the right amount of capacitive reactive power to fully offset those inrush events. And then we do have a little bit of leftover real power. And that leftover real power is generally not a problem at all because it's the 600% inrush that we're fixing, and then that rated real power current that's remaining, the utility system and the whole industrial plant is designed to supply that steady state real power and without creating significant voltage drops. So basically, when we fully cancel the reactive power, we end up fully solving this problem. Same concept, just in a single line format, just to help clarify the concept. Here's a hypothetical motor that's during startup is drawing about 1400 kVAR and 400 kilowatts. So again, dominated by that reactive power. The STATCOM is then automatically injecting its nameplate. In this case, with overload, it's actually topping out at 1300 kVAR. And then we've very nearly canceled all the VARs seen by the utility. So that's during the motor start event where we're trying to cancel those VARs to prevent that problem. And then on the right, we're seeing the motor run condition where that STATCOM then automatically dials back its output to just compensate now the run VARs, which is a lot less. So in either case, the STATCOM is always trying to maintain as close to 0 kVAR to the utility as possible, and always canceling out the reactive current being drawn. So motor start, motor run, fully automated, and fully canceling those VARs as that process is turning on and off. So there's key advantages to this solution of a distribution class STATCOM. The first advantage is what we call site level protection. So because it installs on a medium voltage feeder, it is protecting against any and all motors that might be in the vicinity of that connection. So if you've got 12 motors or 20 motors at a facility, this one medium voltage device is there always protecting for any of those motor starting events for any of those motors, which is a big advantage. No scarce plant space. So because we have the overhead option to be able to fit in the existing utility right away, that allows a plant operator to not alter the plant to solve this problem. We also do have the metal enclosed version that can also go at the plant, but it's nice to have that flexibility to go either way. And in either case, you're not having to get into the actual single lines of the plant like you would with a VFD or a secondary solution. You're leaving that whole plant alone. You're not having to do another arc flash study. You're not having to make new wiring diagrams for the plant. You're literally protecting at the medium voltage side. No real estate procurement. We already talked about that. Because the equipment is so compact, it fits in existing right-of-ways. No routine maintenance because the power electronics have no moving parts and are 100% solid state. And then again, no external harmonic filters. So you're not ever going to come back and say, oh man, I got to filter this thing, or the device itself might have a harmonic problem, unlike the VFDs, which do not comply with IEEE 519. And basically the summary for projects is that you'll have a no surprise implementation because really the technology is designed for the ground up to solve this problem. And you just really install it, and as long as you sized it right, it's going to be solving that problem. Just to summarize now, kind of relative to the traditional equipment that we've explained in terms of cost of implementation. So we've established that soft starters really aren't effective. So they're really not in the toolbox to solve this problem. Reconductoring, because it's a reactive current problem, reconductoring is actually not applicable either. And that's a common misconception too. So reconductoring helps with real power problems, but a reactive power problem cannot actually be addressed by reconductoring. Common misconception. Please take that away too from this webinar. Don't try to reconductor to solve this problem. You'll be spinning your wheels. Large VFDs, we established, are very complex and have substantial harmonic considerations, especially if you've got multiple motors that you need to be compensating. That VFD-based solution is going to get very expensive very fast. And the DVAR VVO, being specifically designed to solve these problems, gives us that nice combination of low project cost, low implementation cost, and very excellent performance for the power quality application. So now we're going to run through some application examples and really show how to apply the STATCOM to a specific motor starting requirement. So we established the basic principle of operation of VAR cancellation. Now, what does that look like to apply that in practice? So in any application, the basic concept here is that we're going to apply the VVO at a medium voltage feeder, and that controller is going to continuously attempt to maintain 0 kVAR to the utility. And so here's an example of a single VVO. A single VVO is able to output up to 1400 kVAR with its overload rating and apply that fully to the motor starting event. So one VVO at 13.8 kV voltage is capable of up to 1400 kVAR of fully dynamic compensation for the motor. This shows an example of what we call our hybrid configuration. And the hybrid configuration takes that single VVO up to 2000 kVAR. So our hybrid is rated with a 600 kVAR external fixed capacitor. And so what's neat about the hybrid is during normal operation is the VVO cancels out actually that 600 kVAR by going inductive. So you still have 0 kVAR to the utility. And then when that motor starts, that VVO is able to swing from negative 600 kVAR all the way up to its 1400 kVAR and then you add that capacitance, which gives you the 2000 kVAR. So a very cost-effective way to scale the solution up to bigger motors when a single VVO won't necessarily cancel all the VARs. We call this the hybrid configuration. We have a 2 VVO solution as well, so it's very scalable. So that's another key advantage of the technology. When you have larger motors, all you need to do is add another VVO. The VVO controls are designed with a technology that allows them to coordinate between themselves and still compensate as effectively as a single VVO. So larger motor, yet that we need to go above that first hybrid step. We just add 2 VVOs, and now we can get up to 2800 kVAR of fully dynamic reactive compensation. And then that same concept of hybrid also applies to this. So I'm not showing it on the single line, but basically we would have one 600 kVAR fixed gap bank on the load side of each VVO. And with that hybrid configuration and 2 VVOs, now we're all the way up to 4000 kVAR. So another very cost-effective way to get up to an even higher motor. You don't have to add power electronics. You're just adding the cost of a fixed cap bank. Very cost-effective. That cap bank is also relatively small. So when it comes to the harmonic sensitivities that we previously discussed, typically a 600 kVAR cap bank or 2 of them is going to be a low enough amount of capacitance that we're not going to run into those problems. So very cost-effective way to scale up the technology and meet those larger motor requirements. One of the questions that comes up with the medium voltage solution naturally is, okay, well, now what's happening in the plant on the secondary? So all of these motors are not connecting right at the medium voltage feeder. They're connecting through some transformer, whether that's a low voltage motor or a medium voltage motor. It's still going to be going through some transformer impedance. So there will be a voltage drop across that facility transformer during a typical motor inrush. This diagram here is showing a typical expected voltage profile at the facility as well as on the feeder when a VVO solution is regulating and protecting the site. So typical inrush event would result in approximately 90% or more remaining voltage on that secondary bus. And that is typically not a problem at all. So really any line start motor is going to be able to tolerate that, no problem. And the real question is if there are sensitive loads on that same motor bus. So if there are sensitive loads on that bus that you're concerned about, and you don't want that voltage dip on the secondary impacting that sensitive load, one of the things we do recommend is just move that sensitive load over to another transformer that the VVO then will be automatically protecting, where that other transformer would not be serving other loads. I'm sorry, other motors that are having that large inrush. So some sensitive loads can be like, okay, the PLC rack that's controlling your whole motor control center, for example, you may not want to have that sensitive. So just simply move that load over to another transformer. That's a very low cost, easy change to make because those are very low power requirements. So basically, we see that the voltage drop across the transformer is generally not a problem at all. And the advantages of having that medium voltage protection really are strong because then any other transformer, any other load on that circuit is fully protected with that medium voltage application. If you do get down around 85% voltage or 80% voltage, that's where you're going to want to look at upsizing that transformer. But typically, when the plant is designed, that consideration is made already. And we often see 90% or above when that VVO is regulating and maintaining the medium voltage at around 100%. Now we'll go through some sizing tables that can be a handy tool for you as you go out and look to solve these problems and apply the StatCom technology independently. So we've come up with a couple of sizing tables. And in this first column here is the horsepower rating of the motor. So all you have to do is know the horsepower rating of the motor, and you can apply this table to solve these power quality problems. Across the top, we just have different configurations that we support that I went through. And so we also introduced this concept of apparent motor size. So because the VVO cancels out the VARs when that motor is starting, it actually has the effect of shrinking the size of the motor. So we call that an apparent motor size. Let's take an example. 700 horsepower motor with a 2 VVO configuration will cancel nearly all of the VARs, such that that motor now, instead of being a 700 horsepower motor in terms of how it looks to the utility, it only looks like a 110 horsepower motor. Much smaller motor means you're not going to have the problem. So that's how to apply the concept of apparent motor size. Our general size guideline is if that apparent motor size is less than 200 horsepower, that's going to give us high confidence that the problem is going to be solved. Just a quick note here, if you have an application that's, let's say, right on the edge. So let's say this example here of you have an 800 horsepower motor, and that's a white cell, not a green cell. Does that mean that I can't solve it? It does not mean that. If that's the situation you face, let us know, and we'll help you we'll review your application and see if that 2 VVO application would actually solve the problem. So we can also do a more detailed study for you if you have an application that you think might be right on the edge there. But by the same token, you're not gonna solve a 1500 horsepower motor problem with this 2 VVO, for example. So it's really, if you're right on that boundary, that's where you'll want to do a little more detailed study and see if you can still solve that problem. And in many cases, you actually can. So a very important note here, this is when there is no soft starter on the motor. The vast majority of our applications, we actually do see a soft starter on the motor. Again, reinforcing soft starters are not going to be solving this problem in general. So we also have a table that provides sizing guidelines when you do have a soft starter on that motor. Because the soft starter does impact inrush by typically about 20–25%, it does allow for the solution to scale up to larger motors. So this is that table, same exact concept of apparent motor size, and we're able to get up to about the 1500 horsepower range now with our standard configurations. If you do have an application for a motor that's larger than 1500 horsepower, we do have a larger substation class STATCOM. Typically, those motors now getting into the 2000 horsepower and up, it's very uncommon that those would be on the distribution system. You do see it sometimes, but a lot of times now you're talking about a larger substation anyway, a larger facility anyway. And the substation class technology that we call our DVAR is going to be most appropriate there. And we've actually solved motor starting problems well into the thousands and 10,000 horsepower range with that substation class technology. So if you can't solve the motor, or if you have a larger motor application, keep that in mind. And we do have a solution for that as well. Same principle of operation, same ability to use overload, just now scaling up to a larger size. So the last portion of our motor starting deep dive webinar is to share some case studies with you. These case studies are based on actual installations of the DVAR VVO distribution class STATCOM. So the first study we'll show is a rock quarry that was causing power quality issues. And one of the key points on this, again, is that there already was a soft started motor at the quarry driving the conveyor systems, and that soft starting motor was not, the soft starter was not sufficient to be able to address this problem. Again, that soft starter was there for mechanical protection, and was not able to protect against the power quality problems. This shows the single line diagram of the circuit. So at mile 0, we have a substation, and about 11 miles out, we have the load that is the quarry here. And there were power quality measurements taken by the utility to track this problem down. And it very clearly shows the motor starting characteristic that was at the quarry. So as you can see with the reactive power and voltage recordings, we see that each of those motor starting events has a corresponding large voltage dip taken, in this case, taken at the secondary side of the quarry. And then approximately a few miles away, there was another power quality recording taken at a customer meter. Had nothing to do with the quarry. And not surprisingly, we see similar voltage dips now happening at that customer. So quarry starting a large conveyor belt, causing power quality issues for dozens of surrounding customers. We took a look at this application, and as I emphasized in the previous portion, really what we need to know is the nameplate rating of that motor, and then we can start scaling that solution based on this. So this was a 350 horsepower motor. It did have a soft starter on it, and that soft starter was set to 75% remaining. And we can see also a couple of other parameters here, but the key ones are knowing that there's a soft starter and knowing what that set point is, and then also knowing the nameplate rating of the motor. A recording that was taken now on the medium voltage side, showing the reactive power that the utility was having to provide prior to having the StatCom installed. So the blue is the inrush of the motor. The red are the VARs that the utility feeder is having to supply. And as we can see that the utility is having to supply all of those VARs. So that's why there is that, in this case, about an 8.5% voltage dip. Again, that's occurring across a fairly large portion of the circuit and impacting dozens of customers. Is that same event now with the VVO StatCom compensating. And so that same blue curve represents the motor inrush. And now we can see that that red curve, which is the VARs that the utility has to supply from the feeder, is now kept at 0 with the StatCom installed near that motor. And so basically that StatCom is fully canceling the VAR loading, and again, a really nice reduction in the voltage dip that is completely addressing that power quality problem. So in this case, it was one VVO StatCom installed on the medium voltage feeder near that quarry and completely addressed the power quality issue. This just shows a zoom in, and what it shows is just how fast the technology is. So the electrical time constant of the motor during inrush is actually slower than the ability of the StatCom to respond. So this sort of ramp up characteristic here is defined by the motor, and we can see that the StatCom is fast enough in its continuous compensation to fully cancel those VARs right from the get-go. There's really no VARs sneaking through even in the early going. So very fast technology, very appropriate to solve this problem. So just a quick summary of this. So there was a motor with a soft starter at a quarry causing power quality issues for dozens of customers. These customers were complaining of dimming lights as well as noisy appliances. And the utility was in a situation where the customer was not comfortable upgrading or changing their equipment. They'd been operating for some years and allowed to connect. So it was really something that the utility needed to do to get to the service quality that they needed for the customers on that feeder. Single VVO completely addressed it. Again, that advantage of being in the utility right away, fully apparent here. So there was no land acquisition cost, no new easements, much like you would install other utility equipment, very readily installed, and that allowed this project to be fully operational in less than 6 months from the time that we proposed the solution to them. So a very fast solution, very effective solution to solve this problem. So the next case study I'll go through is a study now with multiple motors. And this particular operation had 12 larger motors that were spread over about a 4-mile section of a feeder. So it was a chemical processing application where there was a need to pump from an underground aquifer. And in this case, the operator had found it increasingly difficult to start their motors without tripping nearby motors. So depending on the loading of the feeder at the time, depending on the season, they would try to start a motor, and then the voltage dip would be low enough that it would trip off other motors. And again, we didn't need detailed characteristics. We really just needed to know what are the nameplate ratings of those motors, and then do they have soft starters to be able to start sizing up a solution that would fix this problem. Here's an example of a power quality recording that was shared with us. And basically, this is their larger motor starting recording taken on a secondary, showing that on the secondary, it was actually dipping below 70% remaining. On the primary, the dips were about 70% remaining. And that was when the feeder would be fairly heavily loaded in the first place. And then this now large 1,300 horsepower motor tries to start. So by knowing the largest motor and knowing how they're distributed on the feeder, we proposed 6 VVO units on this one distribution feeder. So all of them installed at the medium voltage level, all of them installed in the existing utility right-of-way. And those 6 VVOs had a total output capability of about 8.7 MVAR with their overload rating. And that was more than enough to compensate the expected inrush of the largest motor. That gave us some headroom, but it also gave us and gave the customer a level of redundancy that would ensure a very high availability of protection. So even if a VVO system was having to be, for example, installed or for some reason serviced down the road, you would still have your full ability to compensate no matter what with the 6 StatComs installed. So in other words, 5 StatComs were enough to solve the problem, and that 6th gave them a degree of freedom to compensate for any uncertainties, but also add a level of redundancy. This is just an example of the feeder here. And as I mentioned, the motors are spread over about a 4-mile section of the feeder. And here are the dozen motors. So what we did when we looked at the solution, basically because the motors are distributed, we also wanted to distribute the medium voltage StatComs along the feeder. So there's 2 StatComs associated with this cluster of large motors. And then there's 2 StatComs about 2 miles upstream associated with this cluster of motors. And then 2 more VVOs upstream associated with this initial cluster of motors here. And now this is showing a motor starting event from a large motor and how all the VVOs are responding. So the dotted lines are the voltage dip on the medium voltage side, and the solid lines are the VAR injection of the different StatComs. And you're seeing a variation in the VAR injection of the StatComs because the StatComs that are nearest the motor that's starting are the ones that are putting out naturally the most VARs to compensate. And then the StatComs that are further away are not having to contribute as much to compensate that. And so we took the 70% problem and mitigated that dip substantially down to a 92% remaining problem. This was deemed to be acceptable by the customer. We actually have the ability to further reduce that dip. But for reasons related to how we want to integrate into their system, we decided that it would make sense for the StatComs that are further away, for example, not to be putting out as much for this motor. So still very effective at mitigating the dip, and this performance level was enough to totally address the problems that they were having where they were tripping the other motors. Just another example of an event. Again, we can see the StatComs nearest providing the most output, and the further away StatComs producing less. And then another example, this is now a more upstream motor, and the dip was naturally less because the grid was actually a bit stronger at that point. And then the StatComs that were nearest were compensating that. And so this dip was actually managed to be even down to a few percent of a dip. So in addition to that first case that I showed, where it was really just a 1-for-1 motor, this shows the example of now when you've got multiple motors, in this case a dozen motors, and how flexible that solution at the medium voltage level and how effective it can be. So we had basic knowledge of the motor sizes, and that was enough to determine the solution. This solution was less than 50% of the cost of using VFDs. So if this were to be applying VFDs, you would have had to have a VFD on every single motor, which would have been substantially more expensive, as well as more time consuming, as well as would involve altering the plant, which a lot of industrials would much rather not alter their plant. And then also achieving much superior power quality performance, because the VVOs are there specifically and only to make sure that the whole system's protected, unlike a VFD, which cannot guarantee that. The high-speed data capture functionality within the VVO was a very convenient tool to validate the performance. So we were able to, within weeks of the installation, show, yes, we are solving that problem, and validating the location, validating the sizing, and giving that extra confidence that the problem is solved. And likewise, because this is an apparatus-based solution, we were able to get everything installed and operational in less than 6 months of the initial evaluation of this project, which is very fast. It was by far the fastest option, in addition to being the highest performing option. So those were the couple case studies we wanted to show you. Hopefully, with this webinar, you've been able to understand the motor starting problem better, understand what the limitations of existing automation solutions are, and then build some intuition as to why the StatCom is a really nice fit to solve these problems. So with that, I think we'll open it up for the open Q&A session. Thanks again for listening in, and we'll get your questions addressed now, and we'll also open up the mics. Thanks again for listening in.